This is hexagon. That is hexagon. And all there is hexagon. What is this? This is hexagonal cyclone that occur on Jupiter and Saturn. And this is the beginning of our project. In our attempt to look at earlier study, they covered that it was caused by Rossby wave or the effect of Coriolis force on the fluid in the rotating frame. And the Rossby wave position is frequently near the planet poles, where the magnetic field intensity is strong. Despite the large amount of computer simulation research which explain about this phenomenon, no research has looked into the effect of planetary magnetic field on the shape of gas giant polygon or the Rossby wave, especially in the laboratory before. Therefore, we began to study seriously with the objective of to make an experimental setup in the laboratory and stimulate a phenomenon of polygonal cyclones in Jupiter and Saturn in simulation programs, and to study the effect of magnetic field on a change in characteristics and behaviors of Rossby wave.
So next, let's move to the first part of the methodology, the mathematical simulation. First, we consider the Navier-Stokes equation in a rotational frame with neglected viscosity. To add a term of magnetic force, we modify the equation by adding law-length force. We then get the new value of the angular velocity, which absorbs the term of magnetic field, denoted by omega prime. Then we consider the modified Rossby wave equation, where f, or the Coriolis parameter, was modified to be f prime. Subsequently, from the beta plane approximation, we can find the relationship between beta prime and the magnitude of magnetic field, which is that when beta prime increases, the magnetic field decreases. After that, by following the method of Masonov research, we then get the Rossby wave solutions as shown in the picture. With the condition of a dispersion relation where n is an integer ranging from 0, which satisfies this relation, then we will plot the component of velocity in x and y axis in the polar coordinate, so that we can see the change in characteristics of the Rossby wave by varying n and beta prime value.
For the methodology in the second part, or laboratory experiment, we used an approach in which we approximated the Jupiter's properties by simulating a rotating planet with a rotating tank representing the planet's atmosphere, which is composed of ionized gas with a charged saline solution, modeling the effect of the Coriolis force in a rotating frame observation with a video camera that rotates with the tank like an observer moving with a rotating frame, simulating the planet's magnetic field with a magnet attached to the rotating tank's underside. Then we sprinkle the coffee ground into the saline solution to make it easier to observe the flow of the liquid. We perform the experiment at 39 rounds per minute of rotating speed and vary the magnetic field strength to study the influence of Lorentz force from magnetic field on the characteristic of polygonal vortices. After that, we analyzed the video of the experimental result using PIV lab software. Next, we will move on to the results of our study.
So for the results, in part 1, we constructed the table which depicts the velocity field of Rossby wave in the variation of n and beta prime values. For the n value, it influenced the number of vortices to be higher when its value increases. In the term of beta prime, as it increased while the magnetic field decreased, we can conclude that the magnetic field affects the characteristics of Rossby wave. When there is a high intensity of magnetic field, the position of the vortex shifts toward the pole or the center. The vortex also shrinks in the size. These results can be determined in the following graph.
From the result of laboratory experiment, we found that a change in magnetic field strength affects the characteristic of the waveform. When the intensity of the magnetic field increases, the wave becomes smaller and have a shorter radial distance away from the center. This is consistent with the result of computer simulations. Moreover, there are also waves that constantly change the number of waves, which are consistent with the phenomena occurring on Jupiter. But the waves produced in the laboratory differ from those on Jupiter. This may be caused by a slight oscillation of the spindle in the experimental set and the reflection of the wave on the container wall.
In conclusion, the magnetic field affects the position and size of Rossby wave by when the magnetic field intensity increases, the wave becomes smaller and have a shorter radial distance away from the center.
For future research, we can probably explain the phenomenon in the solar system and of course, in the universe as well.